Hello everyone and welcome to another video. Today we'll finally finish chapter 3. I know it's been a long chapter. I've been dividing it into multiple parts, but here we are, finally gonna be over with it. Again, I just wanna let you know that there is a Telegram channel or a Telegram group for our live sessions so that I can know when they will be held. And if you have any questions, you can ask me there. The link for that group will be in the description. Without further ado, let's just get into it. We'll start with a comparison between ionic and covalent compounds. In the previous videos, we've uh, finished explaining the ionic compounds and the covalent compounds, and we've talked about the simple covalent compounds, right? We talked about the single covalent bonds, the double covalent bonds, and the triple covalent bonds. Today we'll compare between ionic and covalent compounds. Elements in the compound. For ionic compounds we have metals and non-metals. These are the elements in the compound. For example, Na, that's a terrible N, but anyways, NaCl, right? That's a metal and a non-metal. Okay, so these are the elements. In covalent compounds now we have two or more non-metals. Previously we've mentioned that elements can be hydrogen reacting with a non-metal, or a non-metal reacting with another non-metal, right? But in either way, hydrogen is a non-metal, it's a gas. Okay, so here we go. We have two or more non-metals, for example, H2O or carbon dioxide, CO2. Okay, the type of particles. Ionic compounds only have ions, all right? As we've mentioned before, ionic compounds are made of ions only, no molecules. We can't say that we have a molecule of NaCl. There is no such thing in chemistry. We have an ionic compound of NaCl that when made into a solution, it turns into a solution of NaCl, which contains sodium ions and chlorine ions, but no NaCl molecules. Okay, so the ionic compound just gets broken or separated into two parts, a cation and an anion, freely moving. Okay, but there is no whole ionic molecule. There's no such thing. Covalent compounds, no, they are made of uncharged molecules. These molecules can be micromolecules like the ones we've mentioned before with single covalent bonds, double covalent bonds, or triple covalent bonds. Or they can be macromolecules. The macromolecules, we'll talk about them in a second, talk about graphite and diamond, and we'll also talk about silicon dioxide. As for volatility, melting point, and boiling point, ionic compounds have strong electrostatic attraction forces between the cation and the anion. These very strong electrostatic forces are very hard to break. They require a lot of energy, okay? Which means that the boiling and melting points are very, very high, okay? Because the ions are held together by strong electrostatic forces. In covalent compounds, we have low melting and boiling points. Why? Because of the weak intermolecular forces. Let me just hit to the whiteboard to explain this one. Okay, here we have a water molecule made of two hydrogen atoms and an oxygen atom, right? This water molecule is adjacent to another water molecule, okay? These two molecules are connected to each other by very weak forces of attraction called intermolecular forces. From their name, they're intermolecular, meaning that they are in between the molecules. Okay? These forces are very, very weak. If we break these forces, the space between these two molecules will be higher or further. They'll move further from each other. Hence, they will start changing in phase from, say, liquid to gas, which is called boiling. That's why um, the boiling point and melting point for covalent compounds is very, very low. Why? Because the intermolecular forces between the molecules are very weak, so they don't really require a lot of energy to break. Solubility. Most ionic compounds are soluble in water, but insoluble in organic solvents. Covalent compounds are insoluble in water, but soluble in organic solvents. Okay? Electrical conductivity. When we speak of electrical conductivity, we are talking about one of two things: either freely moving ions or freely moving electrons. Okay? If we have either of these, the substance we have will be conductive to electricity. Ionic compounds conduct electricity when molten or dissolved in water. Why? Because the ions are free to move. They do not conduct electricity as solids. Why? Because the ions are stuck in a crystal lattice. If we go back to that structure or diagram, there it is. Here we have the cation, and next to it an anion, then next to it another cation, and so on. Okay? These cations and anions aren't free to move. No, they are stuck in that lattice. They can't move freely, so they can't move the electrical charge, so they don't conduct electricity. That's for ionic compounds, of course. I am not speaking of metals. I'm speaking of an ionic compound. We'll talk about metals at the end of this chapter. Let's get back to the ionic compound. Okay, if we melt an ionic compound or dissolve it in water, what happens? Here we have NaCl, table salt, and I have no idea what's going on. Just a second. I don't know why it does that. Let's just head to our very lovely board, please. Here we have NaCl, our table salt. Alright, in its solid form as an ionic compound, it does not conduct electricity. If we add water to it and we make a solution of NaCl and water, okay, in that case, here's what happens. Let me just magnify that for you. This is how the solution looks like. Positive ion, and very far away we have another negative ion. Here we have a positive ion, here we have a negative ion, and we have water molecules in here and water molecules in here. Alright, we have a whole bunch of positive and negative ions, of course, but just for the sake of time. Anyways, these ions are free to move, alright, which means that they are free to carry the electrical charge, which means that they can conduct electricity. Okay, same thing applies if we melt an ionic compound. That ionic compound in its molten state, in its liquid state, it will be able to move electrical charge. Let's just get back to the notes so that I can find them. Where are the notes? Here we go. That was ionic compounds. Covalent compounds. In general, they aren't conductive in any state, solid, liquid, or gas. They just don't conduct electricity. Why? Because we don't have ions or free electrons, so they don't conduct electricity. We just have molecules, and the molecules, by the way, are uncharged. And I'm not annotating. Great. Are uncharged. Okay? Alright. A small fraction of these compounds dissolve in water and form ions, and these will conduct electricity. So the only case when a covalent compound can conduct electricity is when it completely dissolves in water, forming ions, which means that we still follow the same rule. If the substance can be dissolved and separated into freely moving ions, that's the only case when the compound can conduct electricity. Okay, a small fraction of covalent compounds can do that. For example, hydrogen chloride. Hydrogen chloride, when you dissolve it in water, you have hydrogen ions separated from the chlorine ions, and each of these can transfer the electrical charge. So in that case, it can conduct electricity. Okay, but hydrogen chloride as a gas can't conduct electricity. It's just a covalent compound made of molecules and can't conduct electricity, right? And that was it for micromolecules. Now we'll talk about macromolecules. These are macro from their name. They're giant. They're very big. Okay, they're held together by covalent bonds. Covalent bonds. Sorry. There's a very important definition that we need to talk about, which is allotropes. Allotropes are different structural forms of an element, so we have the same element, in the same state. What does that mean? It means that the arrangement of the atoms is different for the same element. Okay, let me explain. With an example, so we have diamond and graphite. Both of them are made of carbon, that's our element, in a solid state, of course, so it's the same state, same element. Diamond is a crystalline form of carbon, in which each carbon atom is strongly bonded to 4 carbon atoms. That is very important. By covalent bonds, because it's a covalent compound, in a tetrahedral structure. Sounds very complicated, but it's not. It's really simple, actually. It's just a fancy way to say pyramid shaped, that's all. We are supposed to learn how to draw the structure of diamond, because you might be asked to do that in the test. Okay, so here's a simple way to draw it. There is a carbon atom in the middle, and it's connected to, how many did we say? 4 carbon atoms. That's correct. That's 1, that's 2, 3, and 4. That's the structure of diamond, right? Just like that. And here's what tetrahedral actually means. If you try to connect these carbon atoms to each other like that, it will form a pyramid shape with 4 sides or 4 faces, and tetra means 4. So there you go. Hedral means pyramid shape, right? So here we have our tetrahedral structure. This tetrahedral structure gave diamond its physical properties as follows. Diamond has very high melting points, hardest substance known, so it's used in drilling, cutting glass and metals. Doesn't conduct electricity because there are no free electrons. You see, all carbon atoms are connected to each other by covalent bonds. Okay, so there are no free electrons, so it doesn't conduct electricity. It's a colorless crystal that glitter, so we use it in jewelry. Okay, so again, diamond is a crystalline form of carbon in which each carbon atom is strongly bonded to 4 carbon atoms. It's strongly bonded, which means that it's bonded by covalent bonds in a tetrahedral structure. Right, now to the other structural form, which is graphite. In graphite, each carbon atom is strongly bonded to 3 carbon atoms by covalent bonds. It's a strong bond, forming layers of hexagons held by weak forces of attraction, which are called intermolecular forces. Let me explain. Hexagons, intermolecular forces, all are just fancy words to explain simple concepts. We're supposed to learn how to draw the structure of graphite. You might be asked to draw it in the test. So first of all, you draw a hexagon. What's a hexagon? Hexagon is like a B cell, right? It's a shape formed of 6 sides, right? Like that. So that's 1, 2, 3, 4, 5, 6. Okay. And let's just draw another one. Here we go. And another one. Okay. Let's draw another hexagon below it. Why? Because we're talking layers here. In graphite, we're talking layers. So that's one. Another hexagon. And the final one. Okay. Let's just show the carbon atoms in a clear way. These are all carbon atoms. This carbon atom is connected to 3 carbon atoms with covalent bonds. Let me explain, or just that's 1, that's 2, and that's 3. These are the 3 carbon atoms connected to this carbon atom by covalent bonds. Alright? Remember when we said that carbon has a valency 4, which means that it uses for electrons, or it needs for electrons to participate in chemical reactions and complete its outermost shell. Alright? It formed 3 bonds only, which means that there's a missing electron. No, it's not missing. You see this carbon here and this one in the other layer below it, they connect to each other using the electron that's remaining unbound. Okay? Same thing applies here with these two. Here we have this electron, like that. Here you have that electron. Okay? So now we have freely moving electrons, which means, yeah, that's correct, graphite can conduct electricity. It's the only non-metal that can conduct electricity. Okay? This connection between these two layers using these electrons in between, this is called weak intermolecular forces. Okay? So I hope that this clarifies the whole graphite hexagons and stuff, right? Each carbon atom is strongly bonded to 3 carbon atoms by covalent bonds, forming layers of hexagons. Now we know what hexagons are, held by weak forces of attraction. These are called intermolecular forces. Right, so we're talking about 2 layers, 2D layers formed above each other, connected together by intermolecular forces, weak intermolecular forces. Alright, so in diamond, the only type of bonds we had were strong covalent bonds. In graphite, we have 2 types of bonds. We have covalent bonds and we have weak intermolecular forces, which means that we have a different structure and hence different physical properties. The properties of graphite are as follows. It's a black, dark gray, shiny solid. It's soft, which means that the layers can slide over each other, and it's slippery. And that's why we use it in making pencils and as a lubricant. Lubricants are substances that facilitate movement of rotating parts in a machine, like facilitate the movement of gears so they don't friction, right, or to eliminate friction. It conducts electricity, and it's the only non-metal that conducts electricity because the electrons between the layers are mobile, which means that they can move and they can conduct electricity. That's why we use graphite as an electrode in batteries. Now, our last example in macromolecules is silicon dioxide. All right, silicon dioxide, or silica, or sand. In this compound, each silicon atom is strongly bonded to 4 oxygen atoms, and each oxygen atom is strongly bonded to 2 silicon atoms in a tetrahedral structure. Have we ever heard of that word before, tetrahedral structure? Yep, exactly, in diamond, which means that these two, diamond and silica, or silicon dioxide, have the same structure and hence the same physical properties. Okay, because they share the same structure, the same arrangement of atoms, which control the physical properties. Let me just show you how to draw that one, because again we are supposed to learn how to draw silicon dioxide. So here we have silicon in the middle, and here we have an oxygen atom connected to another silicon atom, right? And here we have oxygen, and then another oxygen, and then another oxygen. Same thing as in diamond, we had a carbon in the middle connected to 4 other carbon atoms. Okay, each of these oxygens will be connected to a silicon like that, and we're not gonna be drawing any other things, because if we keep drawing we'll just be infinitely drawing. So that's it, that's the structure of silicon dioxide. Okay, you have to make sure that each silicon is connected to 4 oxygen atoms. Okay, check. and each oxygen atom is connected to 2 silicon atoms, and that's another check. Okay. Now, why is each silicon atom connected to 4 while each oxygen is connected to 2? It depends on the valency. If you take a look at the periodic table, you'll notice that silicon is in group 4, while oxygen is in group 6. Okay, which means that silicon has a valency of 4, while oxygen has a valency of 2. So this is the group, and this is the valency, which means that each silicon needs to bond to 4 oxygen atoms, and each oxygen atom needs to bond to 2 silicon atoms in order to stabilize its outermost shell. And that's why the structure of the silica is in this form. Silicon in the middle, 4 oxygens, each oxygen, 2 silica. Okay? Now, why is the molecular formula SiO2? We'll talk about this in stoichiometry in detail, but I'll let you know how it's made right now. Silicon has a valency of 4, oxygen has a valency of 2. We need to simplify. We can't write the molecular formula like this. If we simplify, this will be 2, this one will be 1. Right? Scissors way, we exchange the valency, and we end up with formula SiO2. And that's how the formula came to be. Right? I actually forgot to mention something while talking about graphite. While drawing its structure, I've just noticed it. So yeah, quickly back to graphite, right? When you draw the structure, you need to let them know that it's an extended structure, meaning that there are other hexagons elsewhere. So how do we do that? We just draw lines like that to show them that this structure is extended. Okay? This structure is connected to other hexagons. Right? That's a very important part that you need to take care of. Okay? So we've talked about diamond, we've talked about graphite, and we've talked about silicon dioxide. And that's it, we're done with the macromolecules. Now let's get to the final part of this chapter, which is metallic bonding. But before that, silica and diamond share the same physical properties we've mentioned. Why? Because both of them have a rigid tetrahedral structure, and all the atoms are held together by strong covalent bonds. Right? So rigid tetrahedral structure and held together by strong covalent bonds. Very well. The uses of silicon dioxide, it's used in sandpapers as it's hard and can scratch the surface. Bricks for building furnaces because of its high melting point due to the very strong covalent bonds in its structure. Making glass and lenses because it's transparent, it's hard and can let light through, right? Okay, now to metallic bonding. It's the electrostatic attraction force between regularly arranged positive and negative ions and a mobile set of delocalized electrons. What exactly does that mean? Sounds mouthful, by the way. Anyways, let's take a look at this structure. Oh, just so you know, we're talking about a metal. We're not talking about an ionic compound. So I'm talking about something like iron itself. I'm talking about something like sodium on its own, alone, not in a compound. Alright? I need you to understand that very well. So, okay, here we have a very disoriented, sick square, but anyways, that's positive. This is a negative electron. That's another positive and a negative electron. Okay, let's talk about sodium, for example, right? Sodium has the configuration of 2, 8, 1. Okay, this one electron is not exactly happy to be in the atom. All right, the attraction forces between the nucleus and this electron is very weak, so it can get loose very easily. Okay, so because of that, The ions or the particles in the lattice exist in this shape. A positive ion surrounded by a sea of delocalized electrons. Right? These delocalized electrons are because of the weak attraction forces between the nucleus and that electron in the very last energy shell. Okay? There's an electrostatic attraction force between this negative electron and the positive ion. Right? It's very normal because this is negatively charged and that's positively charged, so they attract each other. Okay? This attraction force is called the metallic bonding. Right? The metallic bonding is the electrostatic attraction force between regularly arranged positive ions and a mobile set of delocalized electrons. Right? So no negative ions. Right? Okay. The properties of metals. We have delocalized electrons, right? We have freely moving electrons, which means that it can conduct electricity. Right? These electrons can also transfer heat, which means that they can conduct heat. So metals are electricity conductive and can conduct heat. Right? They have high melting and boiling point because of the strong electrostatic attraction forces. Okay? Metals are easily bent and shaped, which is called malleability, and malleability is the ability of a metal to be bent and shaped. Metals can also be stretched into wires, and we call that ductile. They have high density because the ions are very closely packed. Okay, and that's it. We've finished the chapter. So thank you so much for watching, and I'll see you in the next video where we will be talking about the classified. We'll be answering the classified and maybe starting the stoichiometry chapter. I'm not really sure yet. Don't forget to subscribe to the channel and join the Telegram group. You'll find the link in the description. Thank you and see you in the next one.